Hello, I am Aviral. I am going to present the results from our large-scale study of eval in R programs. R is a widely used language for statistical modeling and numerical computation. Apart from being lazy, it supports metaprogramming and first-class environments. R provides a rich reflective interface, with eval being the most prominent example. Eval takes a language expression in some form and returns the result of evaluating it. Since R is a language designed by statisticians for applications in data science, the presence of eval raises a question. Why do R programmers use eval? R has one of the most powerful eval facilities. Consider the use of eval in this function f. It takes two arguments, expr, the code to be evaluated, and n, the environment in which to evaluate expr. Here, expr is bound to the contents of the file code.r. However, expr could also be constructed from program fragments since R allows reflection on code. Env is the environment of the nth caller in the call stack, obtained using parent.frame. It can also be explicitly constructed from data structures such as lists. After the eval, we have no knowledge of what plus will do since eval can redefine it. Eval can inspect the program's call stack as well as the code of any function. Any accessible environment can be modified. This causes static analysis techniques to lose so much precision that they become pointless. This loss of precision can sometimes be mitigated by analyzing the expression passed to eval, but if it comes from outside the program, not much can be done. To address this problem, a group of researchers argued in favor of under-approximating dynamic features. In their words, a practical analysis may pretend that eval does nothing unless it can precisely resolve its string argument at compile time. However, without empirical evidence, assuming that eval does not have side effects or that side effects will not affect results is unduly optimistic. Previous work has investigated eval in web programming, specifically JavaScript web pages. JavaScript's eval behavior was predictable and most eval calls were harmless. While this backed up the soundiness argument, does it generalize to other application domains and to other languages? JavaScript runs untrusted code in a browser, while R is used for statistical computing on desktops. How does this affect eval usage? To answer these questions, we perform a large-scale dynamic analysis of R programs. Our experiment has 4 steps. First, we download R packages and programs from different sources. Next, we extract programs into self-standing scripts. Then we run these scripts against a modified R interpreter to capture eval usage. Finally, we analyze the data for insights. Our approach has 3 limitations. The data we gather is dependent on the coverage of the code. Since the code coverage is 52%, we underestimate the use of eval. We cannot correlate 0.09% of eval calls. This happens when eval is an argument to a higher order function or when it is called from native code. Lastly, we do not record calls to native eval. We have 3 sources of R programs. The first is base. There are 13 base packages shipped with R, providing core language functionality such as package loading. There is hardly any R program that does not invoke them. We consider base packages as part of the language implementation and do not include them in our analysis. Next is Kaggle. Kaggle.com is an online platform that allows users to compete in data science challenges. We acquire 8,000 R scripts from Kaggle. Last is CRAN, Comprehensive R Archive Network. This is an official repository containing 25 years of contribution from thousands of authors, often experienced R developers. CRAN packages have 3 sources of runnable code: unit test, code examples embedded in the documentation, and use cases called vignettes. We downloaded 15,000 CRAN packages and extracted 240,000 scripts for this analysis. Kaggle has very limited eval usage compared to CRAN. There are only 74 eval call sites in 8,000 programs. It is reasonable to expect eval usage to differ between these datasets. Libraries are part of a lively and growing ecosystem, while end-user code is often thrown together, run once, and never revisited. On the other hand, eval is used so widely in CRAN that almost every fourth package calls eval. Overall, we exercise 18,000 eval call sites from 15,000 CRAN packages. There are 49 million eval calls from CRAN. Over a third of our scripts triggered calls to eval. Most CRAN packages use eval modestly. Packages that rely heavily on eval are mostly ones that provide statistical modeling and simulation functions. The R language was intended to be extensible. The combination of lazy evaluation, substitute, and eval are some of the tools given to developers to this end. To understand why developers use eval, we manually inspected the top 117 eval call sites, which contribute to 90% of the calls to eval. We identified 9 patterns of eval usage as shown here. We also identified use cases where the use of eval is overkill. I'm going to focus on one popular use of eval, domain-specific languages. A DSL leverages R's grammar but redefines its semantics in a suitable way. The example here illustrates string interpolation. The glue function from the glue package extracts snippets of code enclosed between braces, evaluates them using eval, and splices their result back into the string. Apart from glue, there are many other popular libraries that leverage eval for different purposes. Our paper covers this in detail. There are many cases in our corpus where eval is not needed, and other, more stylized functions can be used. In this example, the function uses eval to look up a target function name from a constructed string. Then it constructs a call with the arguments that are passed to the current function. Eval is overkill in this case. A semantically equivalent function body can use get to perform the lookup and then call the resulting function directly. However, unnecessary uses of eval are not easy to find and often can only be uncovered by manual analysis. Dynamic analysis is limited due to coverage issues, and static analysis of R remains an open problem. Let's look at how dangerous eval is in R. In our corpus, 6% of eval calls perform side effects from 6.3% of the sites. We care about effects that are visible after a call finishes, that is, variable definitions, updates, and removals. There are 7.9 million writes total. Most of them, 66%, are updates, 31% are new definitions, and 3% are removals. Only 62 sites modify function bindings. This suggests that most side effects from eval are sane. Knowing the environments in which these side effects happen can help determine the impact of eval on our ability to reason about the code. 59% of the sites update the environment specified by the env parameter. The table shows environment kinds where side effects happen. Function environments distinguish between local, the caller environment which is at offset 0, and function, offset greater than 0. Synthetic represents constructed environments. Object is used to denote the environments attached to objects and classes in R's object systems. 39% of mutated environments belong to the immediate caller. Almost half of the sites do side effects in either local or object environments. Some sites receive multiple environment kinds. However, 76% of sites do side effects consistently in one kind of environment. This data suggests that effects from eval are not as widespread and over half of the effects happen in a predictable environment. Overall, 43 functions are responsible for 90% of side effects. Half of those come from just 3 functions. Even though R has a very dangerous eval, side effects from eval are generally not. This gives a ray of hope for a hypothetical R compiler. Even though eval can do anything anywhere, the data suggests most effects are sane. However, the effects can happen in non-local environments, making modular reasoning impossible. Let's investigate how eval usage is different in R compared to JavaScript. We will draw this comparison across 3 axes: the shape of expression passed to eval, the source of this expression, and the environment passed to eval. The expressions passed to eval vary widely. We categorize the expressions based on their shape, which abstracts some of the incidental details. The table shows the 8 most popular expression shapes. 40% of the expressions passed to eval are function calls. This is followed by 27% variable lookups. 50% of these expressions are just simple variable names, which means eval is simply used to look up that variable in a specific environment. Values occur in 16% of sites. 74% of those are constants such as integers. The remainder evaluate to a value. This is followed by subsetting and indexing of vectors and lists. Model fitting refers to the use of model.frame function, which returns a data frame resulting from fitting the model described in a formula. Then we have closure construction. This is followed by local and non-local assignments. These are the most obvious source of side effects. Lastly, we have multi-statement code blocks. They represent a fragment of a program that is evaluated in a particular way in a specific environment. For example, unit testing frameworks take a code block and evaluate it in a sandbox within a try-catch block. Compared to JavaScript, expressions passed to eval in R are more diverse. 88% of the sites in R receive a single shape, compared to JavaScript, in which 98% of sites received only one shape. This makes eval inputs in R less predictable than JavaScript. Let's look at the source of expression passed to eval. We classify expression creation functions into 5 categories. Reflection. These expressions are extracted reflectively from function arguments. R is lazy. Arguments are wrapped in thunks called promises. The substitute function can be used to retrieve their source. String. These expressions are created from strings by concatenation or invoking parse. Constructed. These expressions are constructed using quote. Environment. These are strings converted to symbol using as.symbol, typically to read a non-local environment. External. These expressions are obtained from calls to a native function. Since reflection is the most frequent source of expression, the main use cases for eval involve using substitute to access and transform arguments of a function. Strings correlate with dynamic code loading. Only few calls, 11 in total, consume the result of calling parse on a file. Most build strings programmatically. This data suggests that most expressions come from existing code that was modified by the programmer before invoking eval. In contrast, JavaScript's eval inputs were constants, concatenated strings, or read from DOM. In JavaScript, eval evaluates in local or global scope depending on how it is used. In R, the environment of eval can be specified explicitly. This gives users control over what is visible to the computation started by eval and the potential reach of its side effects. We distinguish between the following kinds of environments. Function. These are environments for the local variables of some functions currently active on the call stack. In 82% of the cases, eval uses its caller's environment, so reads and writes are local. 19% of cases rely on higher call frames, making modular reasoning impossible and code brittle. Synthetic. These environments are built from data structures or constructed explicitly. The parent environment is used to search for variables not found in its child. Side effects stay in the child. Common use cases include the evaluation of an expression in a sandbox. Global. These are environments in which scripts or interactive commands are evaluated. They arise from the fact that our corpus consists of many code snippets that are run at the top level, making global the environment of eval calls. These accidental uses may pollute the namespace for the rest of the program. The eval function is used widely and in varied ways in R. The function is an essential tool for language extension. Its expressiveness invites misuse. Eval is a challenge for automated program understanding. We have observed all sorts of side effects with various degrees of visibility, though most effects are same. Compared to JavaScript, eval usage in R is more diverse and less predictable. Thank you.